to continue from what we have been solving, which is differential calculus. Then what we want to look at here is one of the application of differential calculus in finding the maximum, the minimum, and also the point of inflection of a given function of x. Now here, before we look at this question before us, let's know what they mean by when we have maximum and minimum point of inflection. Now, there is something called turning points or stationary point. So at turning point or at stationary point, we should understand that dy dx here will be equals to 0. That is, we have dy dx equals to 0 at turning point. So that's the first thing to identify here. Then, to now investigate if the turning point is the maximum, minimum, or point of inflection, we need to take the second order derivative. That is, differentiate again with respect to x. Then, what we have in the second derivative, which is the square y, the x squared, will determine the nature of that turning point. Now, the turning point we have here, we are going to solve this equation after equating it to 0. So the values of x we have here, then we substitute that into the second order derivative. And when the second order derivative is less than 0, after substituting the value of x, which is the turning point, then this here, that point here, we will know as the maximum point. So we are going to have maximum point. That is, if after we substitute the value of the turning point in the second order derivative and the result is less than 0, it implies that that turning point substituted here is a maximum point. Now, if the second order derivative, the square y, the x squared, is greater than 0, after we substitute the turning point, it implies that that turning point is a minimum point. Is a minimum point. And if it is equals to 0, that is the second order derivative, the square y, the x squared. If this is equals to 0, after we substitute the turning point, it implies this turning point here will then be a point of inflection. A point of inflection. So that's what we have. Then let's demonstrate this with what we have on the board. That is, for the first question here, investigate the nature of the stationary value or turning point of the following functions. Now, for the first one, we have the solution as follows. Now, the first thing here is to get the turning point, which is also the stationary point. From what is given here, which is y equals to x cubed over 3 minus x squared minus 3x. Then we need to differentiate this. That is, we find derivative. So dy dx here will then be equals to, this becomes 3x squared over 3, then minus 2x minus 3 here. Then here, 3 cancel each other, and this same thing as dy dx equals to x squared minus 2x minus 3. Then at turning point, this will be equal to 0. So at turning point or stationary point, we have the y dx equals to 0. Then therefore, what we have here, we equate that to 0, and that means we have x squared minus 2x minus 3 equals to 0. Now, here we have a quadratic equation that we can solve by, just factorizing there. So here, what will give us minus 2 and will give us minus 3. So that will be minus 3 plus 1. So we have x squared minus 3x plus x here, then minus 3 equals to 0. So here we give us minus 2x, and also the product, the minus 3x squared. Now, from here, it implies this gives us x into bracket x minus 3, then plus 1 into bracket x minus 3 equals to 0. That is, here we have x minus 3 into bracket x plus 1 equals to 0. So when we solve this now, we have either x minus 3 equals to 0, or we have x plus 1 equals to 0. That is, what we have here, x equals to 3 on this side, and here x equals to minus 1. Now we have two turning points. We have the first one, x equals to 3, and the second one, x equals to minus 1. Now let's investigate now to know whether this is maximum or minimum, or this is maximum or minimum. Now it implies we take the second, the other derivative, that is, we have the square y dx squared from here. So differentiate the first order derivative to get the second order, which implies here this will give us 2x, then minus 2, then 0 for minus 3 here. So this is the second order derivative. Now, at point x equals to 3, that's the first turning point. Now, let's substitute 3 here. So it implies that the square y, the x squared, here, when x equals to 3 here, becomes 2 times 3, then minus 2, which implies this is 6 minus 2, which implies this is 4. And 4 here is greater than 0 from here. Then we should understand that when it is greater than 0, that is when the square y, the x squared, is greater than 0, what we have there is a minimum point. So now we can say, therefore, since the second order derivative here is greater than 0, then x equals to 3 is a minimum point. Is a minimum point. Then we can use that minimum point to get the minimum value, because there is a difference between minimum point and minimum value. So the minimum value now will be when we substitute the minimum point into the given equation here. So we can substitute there to get the minimum value. Then investigate the second point as well. Then at point x equals to minus 1. So also the second order derivative now, we substitute x equals to minus 1. Then the square y, the x squared, will then becomes 2 multiplied by minus 1, then minus 2. 2 times minus 1 here, that's minus 2, then minus 2, which is equals to minus 4. This is less than 0. And when it is less than 0, so when the square y, the x squared, is less than 0, we have maximum. So when it is greater than 0, we have minimum. So therefore, here we can conclude that x equals to minus 1 is a maximum point. Then, which implies that the maximum value of this function will be when we substitute the maximum point into the given function. And that is that for the first one. So I believe you are learning from here. Please, you can show that you are, gaining from here by giving thumbs up and share this video. God bless you. Thank you. Now let's look at the second one. From what we have here, the same step. We first get the turning point. After getting the turning point, then we investigate that by substituting that into the second order derivative. And if the result is less than 0, it means you have maximum point. If the result is greater than 0, that is the square y, the s square at turning point is greater than 0, we have a minimum point. Then if it is equals to 0, we have a point of inflection. Now, okay, that is when the square y, the x square, is equals to 0, we have a point of inflection. Now, the second question here as well, very quickly. From what we have, y equals to x raised to power 4 minus 4x cube. Now, from there, the turning point as well, that's the first thing. So, number 2, we have y equals to x raised to power 4 minus 4x cube. Now, we have dy dx. Derivative of this becomes 4x raised to power 3, then minus 12x squared. Then, since we know that at turning point, dy dx will be equals to 0, then what we have here, we equate it to 0, and we have 4x cubed minus 12x squared will then be equals to 0 on this side. Then solving this equation here now, we can factor what is common. 4 is common, s squared is common. That means 4s squared out. Then here remain x, then minus 3 here remain equals to 0. Now, these two multiplies. Either of them could be 0, so we can say 4s squared equals to 0, or we have x minus 3 equals to 0. Now, from here, divide both sides by 4, s squared is still equals to 0. Take the square root on both sides, x equals to 0 and here. Then on this side, we have x equals to 3. Which implies here we have two turning points. We have the first one, x equals to 0, and the other one, x equals to 3. Now, which one is this one? Is it maximum, minimum, or point of inflection? And this one as well. Now, to investigate the nature of the turning point, we take the second order derivative. That is, we find the square y dx squared. Now, at this point now, when we differentiate from what we have here, the square y dx squared, differentiate this again now. That is, differentiate the first derivative again, and this becomes 12x squared minus 24x. Now, here we have the second order derivative now. We can then test for the first point. So at the turning point, which is x equals to 0, then our second order derivative, which is the square y dx squared, will become, so we put 0 for x here, and this becomes 12 times 0 squared minus 24 times 0 here. So everything here is 0 minus 0, and which is equals to 0. Now, when we substitute x equals to 0, the second order derivative here is equals to 0. That means this point here will then be point of inflection. So therefore, we have x equals to 0 here is a point of inflection. Is a point of inflection. So that's the nature of this point. Now, for the point x equals to 3 here. Also, we substitute that into the second order derivative. That is, at x equals to 3, the second order derivative, which is the square y, the x squared will become, so we substitute 3 here, and we have 12 into bracket 3 square, then minus 24 times 3. Then from what we have here, this same thing as 12 times 9, 3 square is 9, then minus 24 times 3 there, we have 72 from here. Then we have 12 times 9, that's 8. Then 108 here, that's 108 minus 72. And when you subtract 72 here, that gives us 6. That's 36 from here. That is, what we have here now is, of course, greater than 0. So this is greater than 0 here. That means when the square y the x square is greater than 0, we have a minimum point. That's what we have, minimum point. So we can then say, therefore, x equals to 3 is a minimum point. And we can also get minimum value by substituting x equals to 3 into the function given. So that will give us a minimum value. So that's how to, investigate the nature of the turning point. Finding maximum, minimum, and point of inflection. I appreciate you for joining so far. You are watching my starting math class. Now let's solve the third one. I believe somebody can try that now. Now let's look at the third one together. So also, the first thing to do is to find the turning point. That is, the stationary point, the y dx is equals to 0. So here, number 3 now, we have y equals to x cubed minus x squared minus 5x. Now, the first thing we do here is to differentiate with respect to x. So the y dx is equals to, here we have 3x squared minus 2x minus 5. That's the derivative. Then at turning point or at stationary point, we understood that the y dx will be equals to 0 at turning point, which implies that we equate this to 0 here, and we have 3x squared minus 2x minus 5 will then be equals to 0. That's the turning point, which implies we have a quadratic equation here. So we can solve this and we'll factorize. So this gives us minus 15x squared. Then the factor of minus 15 that will give us minus 2 here, that should be minus 5x plus 3x. So the quadratic equation here becomes 3x squared minus 5x plus 3x, then minus 5 equals to 0. Then what is common between these two? We have x common. So what is left here? That's 3x minus 5 here. Then plus 1 common here. That's 3x minus 5. Then equals to 0. So here we have 3x minus 5 into bracket x plus 1, then equals to 0. So is either 3x minus 5 equals to 0 or x plus 1 equals to 0. So on this side, we have 3x equals to 5. Divide both sides by 3, x equals to 5 over 3. Then on this side, we have x equals to minus 1. Now here we have two turning points. Now let's investigate the nature of those turning points. It implies we find the second order derivatives, that's the square y, the x squared. And this here, that means we differentiate the first order derivative again, and we have 6x here minus 2, then plus 0, that's 6x minus 2. Then at turning point, the first one, which is x equals to 5 over 3, so at x equals to 5 over 3, now the second order derivative becomes, that is the square y, the x squared, will be equals to 6 multiplied by 5 over 3 minus 2. And here 6 can go, 3 goes here 1, 3 goes here 2. 2 times 5, that's 10. 10 minus 2 here, that's 8. And 8 is greater than 0. Now, when the square y, the x squared, is greater than 0, we have minimum points. That means, since this is greater than 0, therefore, x equals to 5 over 3 is a minimum point. So this is the nature of that point, minimum point, and which implies that here we can find the minimum value and substitute the minimum point in the function given here. Now, also the second point, which is x equals to, at x equals to minus 1 now, then we have the square y, the x squared becomes 6 multiplied by minus 1, then minus 2. And 6 times minus 1, that's minus 6 minus 2, which implies we have minus 8. And this is less than 0. And when the square y the x squared is less than 0, it means we have a maximum point. That is, therefore, x equals to minus 1 is a maximum point. Then we can get the corresponding, maximum value by substituting x equals to minus 1 into the equation there. So we have already looked at these three, questions, and investigated the nature of their turning points. If you are just joining us, this is Master T Math class. You can check our previous live classes on this particular topic, differential calculus, in order to have some understanding of differentiation. And thank you. Subscribe. We upload video daily here, so subscribe and give a thumbs up. Share this video to support us. Thank you. And if you want extra lesson, maybe for your children or something like that, you can contact us on +234 7037 79 7570 on WhatsApp. You can send your message and we attend to you. And thank you. We appreciate you for joining us. See you again next class, and bye for now.